When a new AI model drops, engineers often treat latency as a software bug to be fixed with better code or compiler flags. But what if that delay isn't an error at all? What if you were fighting Einstein's laws instead of your own stack? In distributed training clusters costing millions, chasing microsecond optimizations can burn budget on problems physics forbids us from solving. Today we connect that headline to the hard engineering trade-offs behind speed of light limits and why moving data is often more expensive than computing it. The counterintuitive reality for most teams is this: you are wasting money optimizing code against a wall that does not exist in software, but only in physics. We treat latency as a failure of our algorithms, yet every bit moved across copper or fiber incurs a bill we must pay. The question isn't why your cluster runs slow, it is why you expect it to run at the speed of light when data physically has to travel through space. Consider the premise that engineers are chasing zero latency as if it were a configuration error. If you optimized every line of PyTorch code perfectly, would your GPU cluster suddenly operate instantly? The answer lies in the time it takes a photon to cross a room. Even with perfect software, data traveling 2 meters through fiber optic cable incurs a hard latency floor. This is roughly 10 microseconds for round-trip signal propagation plus electronic switching time. You cannot write faster code than light can travel. This fundamental ceiling has led many teams into expensive dead ends. A recent benchmark suite called solvable, released in March 2026 by researchers at Stanford and NVIDIA, tested 235 real-world CUDA kernels against this theoretical limit on next-generation Blackwell GPUs. The results were stark. Even the most optimized production code lags significantly behind physics because of energy costs and physical distance, not software inefficiency. They analyzed 124 production AI models across 6 distinct architecture types, including language, diffusion, vision, audio, video, and hybrid systems. In every single case, the gap between what engineers achieved and what is theoretically possible was vast, yet closing that gap required exponentially more power rather than better logic. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand this properly, we need to stop looking at performance as just flops or memory bandwidth. We must look at where data comes from. A new framework called Solar, released in June 2026, automatically translates code into a cache-aware analytical model. It calculates the absolute minimum execution time allowed by hardware geometry and physics. This tool revealed that current optimizations often leave orders of magnitude of headroom simply because engineers are optimizing for relative speed rather than hitting the absolute physical limit. Solar proved zero violations against these theoretical bounds in testing, confirming that faster is now a matter of distance management, not just clock cycles. This shifts our entire approach to system design. In distributed AI training, reducing latency further requires exponentially more energy and money. As shown in the analysis of the benchmark suite, chasing micro beyond the light speed limit is an economic loss. The latency we see isn't a failure to optimize, it is the cost of moving data across physical space at scale. If your team is obsessed with shaving off nanoseconds through software tweaks, they are burning budget on the wrong problem. We have seen this misdiagnosed performance issue in community logs from projects like llama.cpp, where users were baffled by GPU speeds matching CPUs for specific inference tasks. The root cause was often not chip speed but data movement bottlenecks or memory bandwidth saturation, where the physics bill for moving large tensors outweighed compute gains. Similarly, discussions on undervolting reveal that without managing power limits and thermal caps, pushing clocks higher yields diminishing returns due to heat dissipation physics. You cannot simply force silicon to move faster than its cooling system can handle, nor can you make data jump across a rack instantly. The practical takeaway for the AI practitioner is simple: stop treating latency as a software problem you can fix with better algorithms alone. If your cluster feels slow, look at topology and cabling first. The gap between your code's speed and reality isn't in your loops, it is often in that 2-meter fiber patch cable connecting 2 racks. For system designers, the architecture decisions regarding where GPU A sits next to GPU B versus across a rack have a harder impact on latency than any kernel optimization you could write. The speed of light limit is real, and you can only approach it by minimizing physical distance or accepting massive energy costs. Engineers who understand the difference between computational limits measured in flops and communication limits governed by light speed are the ones designing viable AI clusters. The ability to explain why optimizing for 10 times faster is impossible without changing hardware topology will make you a more authoritative engineer in distributed systems interviews and design reviews. In summary, we stopped treating latency as a bug and started measuring against Einstein's laws with tools like solvable. We found that the gap between our optimized kernels and light speed often costs millions in energy to close. The lesson is clear: stop chasing microsecond optimizations that cannot overcome fundamental physics bills. Focus on topology, distance management, and understanding where your data actually travels before you write a single line of code for optimization. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.